16 miles, and it's a circular
Yeah.
sort of a building.
Yeah. Well, it's a big tube. I mean, you think basically it's mainly under France and partly under Switzerland, and it accelerates protons around in a circle, both ways. One beam goes one way, one goes the other way, and they go around 11,000 times a second. So that's very close to the speed of light, 99.99999% the speed of light.
Newton was able to go from Earth to the moon because he understood gravity well enough, even if it would make you laugh to think that you could fly to the moon and return with just little resources. Everything in our planet is perfect. Even after years of research, certain mysteries remain unsolved despite the fact that there are models all over the world. Why does time flow only in one direction? What is the truth? Why is there gravity? Why does time slow down when traveling at the speed of light? For millennia, this question has captivated us. What if I told you that gravity doesn't exist? The human intellect created it totally. That may seem improbable, yet that's what famous Dr. Brian Cox recently claimed. Let's look at the nature of gravity and the causes of time's delay in recognizing its negative effects. We must look past Newton. The problem is not what he understands, but what he is unable to do. One of the problems with Newton's theory of gravity is that it only predicts how an item will move when subjected to its own force. It does not explain the mechanics of gravity or its existence. It only makes you count, and Newton knew that. The most important thing is that it comes only from Allah. The sun, planets, and comets, all of nature's most beautiful creations, are said to operate solely in compliance with the wisest rules and decrees. In other words, I'll give you the tools to understand how things operate, but don't ask me how or why. That's God's job. There are many unsolved mysteries in the vast universe in which we inhabit. This list of mysteries includes several fascinating occurrences related to time and gravity, two fundamental aspects of human existence. Imagine a world in which time is strange and uncertain, and the forces that hold us together are different. This is where Albert Einstein's theory of relativity and our understanding of time and gravity divide. The well-known Albert Einstein, whose theory of relativity altered our understanding of the cosmos and opened our eyes. Their work forms the foundation for our understanding of how time works in different situations, particularly when we are moving quickly. It all started when Einstein proposed the two fundamental theories of special and general relativity at the start of the 20th century. The theory of special relativity changed our understanding of space and time, since it was published in 1905. In essence, it tells us that all non-accelerating observers are bound by the same set of physical laws, independent of velocity. The theory incorporated the concept of social interaction in addition to the well-known idea that time slows down or speeds up depending on the situation. One of the best hypotheses to explain time dilation is the light clock. Imagine everything in a spaceship moving at a remarkable velocity, nearly as fast as light. A light beam perpendicular to the direction of motion is reflected by two mirrors in the spacecraft. When viewed from a plane, light travels in a straight path after bouncing vertically. An outside observer who is not flying with the aircraft, however, perceives things differently. When they saw the swift aircraft, they followed the path of the beam. Because the airplane is moving, the beam must travel farther to hit the mirror. According to the laws of physics, the speed of light is always the same for every observer. The beam should thus resemble a long diagonal path. Now things start to become interesting. The beam must travel for the same length of time for viewers inside and outside the airplane. However, because the journey to the external observer is longer, the light takes longer to reach its target. Einstein used the term time dilation to characterize the apparent time difference between two observers. How long does it take the observer to get close to the observer who is not moving? Therefore, depending on what you do in this case, the time changes. This is not only a theory, since these experiments confirm the societal influence. For example, particles may move at almost the speed of light in particle accelerators, such as the Large Hadron Collider. To get accurate measurements, researchers must take time dilation into consideration. Special relativity allows for a cosmos in which time is infinite and may be compressed or stretched to one's liking. It makes us rethink our typical thought patterns and acknowledges how vast the universe is in comparison to our own experience. Einstein's theory of special relativity, which was first put forward in 1905, fundamentally altered our knowledge of the structure of the world, especially in relation to motion and time. Critical theory shows that the same set of physics applies to all non-accelerating observers, regardless of velocity. To have a better grasp of special relativity, let's examine its foundations. One of the tenets of special relativity is the notion that light travels at the same speed for everyone, regardless of velocity. Regardless of your speed, the apparent speed of light is always the same, at about 299,792,458 meters per second. This idea runs counter to the widely held belief that motion makes us move more quickly. The speed of light appears to be the limit of the universe's velocity. Because of special relativity, we believe that simultaneous events do not occur for everyone at the same time. From a different perspective, if two events are taking place in different places and you are moving in their direction, what you see happening at the same time won't happen to someone else. This concept defies our understanding of time and initially appears strange. The time dilation hypothesis is one of the most important and useful ones. As we covered in the last part, time will either slow down or lengthen as you walk. As you go faster, time seems to go more slowly than it would to a stationary observer. This effect will become increasingly apparent as you approach the speed of light. Consider having two identical twins, one on Earth and the other traveling across space at the speed of light. When the twins return, they will be younger than their siblings on Earth. This phenomenon, commonly known as the twin paradox, is caused by real-time dilation. This disparity is caused by the speed of light constant. As they approached it in little steps, the twins noticed the clock ticking away as usual. However, as the twins travel the world, it appears to Earth viewers that their spacefaring clocks are slowing slower. Another consequence of special relativity is length contraction. A fast-moving object seems short in the direction of motion to a stationary observer. This effect gets increasingly apparent when things get closer to the speed of light. It's really slight at regular speeds. One of the most famous equations in physics, E equals mc squared, is a direct consequence of special theory of relativity. The interchangeability of mass and energy is illustrated by this formula. This suggests that mass and energy might be converted into one other. To understand how materials react at high speeds and how energy is produced during events like nuclear strikes, one must grasp this concept. Special relativity is more complex than it first appears. There is useful information available. GPS systems, for example, rely on precise satellite transmissions. However, when the satellites get closer to us, the time dilation effect takes over. If GPS calculations do not account for the effects of certain connections, our navigation system will become less accurate. Special relativity forces us to reevaluate our conceptions of time and space. It illustrates how the universe operates in a manner that is incompatible with modernity. Time is not an absolute concept, rather, it is a relative one that is affected by movement. The speed of light and the relationship between mass and energy are two important ideas that have been proven true by countless experiments. Let's go on to Albert Einstein's general relativity concept from 1915. This theory presents the idea of gravity and demonstrates the connection between gravity and the structure of the Earth. Essentially, the conventional view of gravity as a force dependent on mass distance is disproved by general relativity. Instead, it represents gravity as the curvature of space-time. It's not as hard as it seems to grasp. To understand general relativity, we must view the universe as a four-dimensional entity with 3 dimensions of space and 1 dimension of time. In 4-dimensional space-time, you may create enormous objects like planets and stars, and even bend space-time itself to make room for them. This curvature is what we call gravity. Think of space-time as a huge, pliable structure. This fabric would shatter under an object the size of the Earth. For instance, when a ball is placed near the soil, it rolls into the trenches. This is similar to what happens when something encounters gravity. This is not a mystical force, but just a question of following the curvature of space-time. general relativity provides a convincing explanation for how the solar system's heavenly bodies move. It accurately predicts the orbits of the planets, including the Earth's elliptical path around the Sun, compared to the antiquated idea of gravity acting as an attractive force. Curved spacetime offers a more thorough explanation of orbital motion. One of the most famous findings of general relativity occurred during the solar eclipse in 1919, when Sir Arthur Eddington led an expedition to study the bending of stars caused by the Sun's gravity. The idea states that light from the trajectories of distant stars is bent by the Sun's vast presence, making them appear somewhat out of place. In contrast to Einstein's predictions, observations obtained during the eclipse supported the notion. Motion, like gravity, affects time, according to special relativity. In regions with strong gravity, time travels more slowly than in regions with weak energy. This suggests that standing near a large object, such as a black hole, will cause your watch to run more slowly than standing farther away. General relativity was the first to suggest the idea of the black hole, the site of the greatest challenge. The gravitational pull of a black hole is so strong that nothing can escape its entrance, not even light. The point of no return is the event horizon, which is the boundary around a black hole. Anything that crosses this line will be pulled into the black hole. General relativity also has a major effect on the structure of the entire universe. Einstein first included cosmic constants in his equation to preserve the staticity of the cosmos. However, he regarded the realization that the universe was expanding as his biggest mistake. The expanding universe theory, supported by general relativity, is the foundation of the Big Bang hypothesis, which explains the universe's genesis. One essential element of general relativity is the existence of gravitational waves. These are rippling phenomena in space-time caused by enormous objects, like as merging black holes or neutron stars, that accelerate quickly. Another part of Einstein's theory was confirmed in 2015 when the Laser Interferometer Gravity Wave Observatory made the first direct detection of gravity waves. Tests of general relativity have been conducted over the years, and each time they have been successful. The real orbits of planets, the bending of stars, and discoveries of gravitational waves have all consistently confirmed this theory. Given how we perceive gravity in our daily lives, the idea that gravity is a fiction may seem shocking, even contradictory. In the realm of physics, however, there is always room for debate, speculation, and the exploration of conflicting theories. It is common for scientists to challenge conventional wisdom. The traditional thinking of gravity is contradicted by a number of theories. Their disagreements revolve around opposing theories, some of which aim to replace or change what we know about gravity. One of the most popular alternative theories is called modified Newtonian dynamics, MOND. It illustrates how gravity behaves differently than one may anticipate from ordinary Newtonian gravity at low acceleration. MOND contends that a reference to darkness is not necessary to explain the behavior of galaxies. Instead, MOND proposes that gravity accelerates to very high speeds. Dark energy and dark matter are the main points of contention in the gravity issue. The rotation and expansion of galaxies are among the many cosmic phenomena that have been explained by these mysterious hypotheses. The conventional explanation of gravity's detractors argue that dark matter and dark energy are unnecessary and that other theories sufficiently explain the findings. Not all academics agree that Einstein's theory of relativity is deficient. They suggest that there may be more important, unknown, or powerful forces at work that might change or improve our current understanding of gravity. These researchers are considering a variety of possibilities, including theories that suggest unique interactions or traits. It should be noted that the alternative proposal was not immediately abandoned. The scientific community tests these hypotheses rigorously to determine their effectiveness. Although several competing theories have been proposed so far, none are believed to change the nature of gravity. It is important to emphasize that sickness and ambiguity are important aspects of study. It is helpful to question conventional wisdom and take into account other possibilities when seeking information. Uncertainty and investigation lead to science. Questioning the scientific consensus can lead to additional inquiry and a better understanding of the universe. Despite competing in other theories, the explanation of gravity provided by general relativity remains the most important and successful theory. This is because it is consistently subjected to stringent testing and accurately describes phenomena such as Earth orbits and star bending. General relativity's simplicity and comprehensiveness make it difficult to change. As we discussed time dilation, the concept that time behaves differently with energy is introduced by Einstein's theory of special relativity. Now let's examine this theory's applications and real-world ramifications, especially as they relate to destination travel. The exploration of space has long piqued people's attention. Our dream is to visit other planets, stars, and perhaps galaxies. The size of the globe and the speed of light, however, are the two main barriers to traveling very far from Earth. According to Einstein's theory, the fastest speed in the universe is the speed of light in a vacuum. The fastest thing that can move is the speed of light. This limitation is a major barrier to interstellar travel since, even with the most advanced equipment, it takes a long time to approach the closest star. To further understand what time dilation and space travel means, let's examine the famous twins. Let's say that one twin remains on Earth while the other twin moves to a distant star at a speed far slower than light. The twins will learn that they have had a shorter life than their siblings when they return. The future was reached by the twins who traveled across space. Travelers place a great value on time. The farther one travels, the more time dilation occurs. Astronauts may age more slowly than people on Earth due to the considerable time dilation impact of traveling to nearby stars. This may seem like something from a science fiction book, but the real cause is social theory. Imagine a day when humanity sends large expeditions to a nearby star. Because of the distance, it can take decades to travel even a small fraction of the speed of light. The astronauts on board will see the journey as shorter due to time dilation, but the planet they depart from will be older. Time dilation affects not just biological beings, but also technology. For instance, time dilation needs to be regulated to ensure the precision and correct functioning of computer systems and communications equipment on airplanes. There are several challenges in the fast-paced world of social media travel. Those who serve in this role have to consider the effects of lengthy isolation, cosmic radiation exposure, and the psychological effects of being isolated from the world for extended periods of time. The effects of time dilation are already evident in daily life, even though space travel to distant stars is still a promising future. Because it uses the Global Positioning System, GPS, its location is determined by the accuracy of satellite signals. As the satellites get closer to us, time dilation is having an impact. The accuracy of the navigation system will suffer greatly if the social aspects are not taken into account when GPS calculations are made. Now let's explore the question of why time only flows in one way. The concept of time governs both our lives and the universe. It informs decisions made in the past, present, and future. This lonely journey from the past to the future is the essence of human existence. So why is there a time route? The concept of entropy is essential to comprehending why time moves in a specific way. Entropy is a measure of the disorder or unpredictability of a system. It is a basic concept in physics and has to do with the arrow of time. Put otherwise, entropy is a measure of the degree of chaos or unpredictability that exists throughout a specific period of time. The relationship between entropy and time direction is explained by the second rule of thermodynamics. This rule states that in an isolated environment, the total entropy will either increase or remain constant. In other words, entropy tends to increase naturally rather than decrease. Entropy is present everywhere and has clear consequences. Take, for example, a neatly stacked deck of cards. If we shuffle the cards, they become arbitrary and out of order. The entropy of the shuffled deck is larger than that of the starting order. Things go from organized to chaotic as you move the arrow of time. The existence of different work hours during different phases of life. The increase in entropy is noticeable at the macro level of our daily lives. We make the issue worse by looking at ice that has dissolved in water or the ingredients in a cup of coffee mix. The one-way flow of time is represented by this macro process. We see that the laws of physics are symmetrical with respect to time in the realms of atoms and particles. This suggests that, at the microscopic level, the process is reversed. When you watch the accident tape and play it again, you won't notice the difference. This phenomenon is known as time reversal symmetry. The seeming conflict between irreversibility in the wider cosmos and reversibility in the microscopic world arises from the concept of initial conditions. Numerous entities and their interactions make up the macroscopic cosmos. The first event in this complex world was the origin of the arrow of time. From past memories to current and future expectations, our brains process information in a sequential fashion. The idea that time is always evolving is not unique to physics or the universe. Time truly exists in a very similar fashion to how we see it in the outer world. The unidirectional nature of time also raises important questions about reality. It assesses our ability to reason and our understanding of cause and effect. We tend to think of the past as fixed and the future as boundless. Our perceptions and judgments are influenced by these physical patterns. The existence of time is the foundation of our existence. It advances our understanding of the universe, our knowledge, and our personal growth. If time didn't exist, our world would be very different. Our actions won't have any consequences, and there won't be any cause and effect. Thank you for watching the Voyager episode this week. While you're here, click on the video to see more exciting videos like this one.